I was on mute that whole time. For those of you who are just joining us, we should be working on our Unit 1, Day 5 warm up, which is located under our Unit 1 module. So you should be in Canvas, Unit 1 module, Unit 1, Day 5 warm up. We've got about 3.5 minutes left to do that. Okay, so just as a reminder, whenever you're not able to get something done in the allocated time during class, you will have the opportunity to finish it before the end of the unit. So all of this Unit 1 work will be due on September 1st, which is this coming Tuesday. All right, so we've got a weekend coming up, obviously. I want you all to go ahead and relax and recuperate. And I also want you to be productive with your time if you know that you still have some outstanding assignments that have not been completed. But, obviously tend to yourself, make sure that you're taking time away from schoolwork, away from a computer screen, but also don't fall behind. And this is why we want to establish a good habit of doing just a little bit each day so that we don't have it all piled up at the end of the unit. Okay. So today's lesson is going to explore enzymes. But before we do that, I want to show this table one more time just as a reminder. This is the bang for your buck table. That's the name that I've given it. And essentially what I mean by that is the information that you can find on this slide in this table is ultimately going to put you in a good position to be successful in this unit. So I'm going to leave this up for maybe 10 more seconds, hopefully over the last 2 days, because we've looked at it every day, Wednesday, Thursday, and now Friday. Hopefully over the last 2 days, you've had an opportunity to copy this information down in your notebook or to reproduce this table in your own Google Doc or Google Slides. But this is where we really want to hone in. This is the information that we should be remembering. And as time goes on, I do want you all to start to establish these patterns in your head. It's not all going to happen right away. And I had a conversation with a few of my students yesterday about them feeling a little bit discouraged. But I don't want you all to be discouraged because this stuff takes time. There are a lot of new concepts here, a lot of new words. Even for me, I've taken several biology classes over my lifetime. I have taught biology several times now, and some of these terms are still difficult to pronounce. I still get them a little confused at times, and that's just because we're human. We make mistakes, but don't be discouraged because we're just starting the school year. And ultimately, if you can be confident and if you can really work hard to learn these things and start to make connections between these concepts, you'll be in a great position to succeed going forward. All right, so here's the bang for your buck table. Hopefully you have it, and we'll jump into today's lesson. Can I have someone please volunteer to read the objectives for the day, or the objective?
Explain how environmental factors can affect whatever that word say function.
Enzyme function. Thank you, DeMarco. Today, guys, DeMarco has been contributing a lot to our class. Um, I've also gotten a lot of contributions from Kyrie, who's not here today, Joseph. I want to hear some new voices, okay? So please do not feel, embarrassed if you don't know the answer 100%. A person who's willing to put themselves out there and at least give it a try, in my eyes, is just as worthy of praise as someone who is going to be able to get the answer right. All right, so even if you're wrong, it's going to help everybody else learn. And I can guarantee you, you are not the only one who is not confident about all of your answers at this point. So please open up and share. I appreciate DeMarco for being the one to read. Can I have somebody else read the essential question, please?
What does it mean for enzymes to have an optimal environment?
Thank you. Thank you, Joseph. So what does it mean for enzymes to have an optimal environment? Perhaps we know what the word optimal means. So we'll be thinking about that, especially as we approach the end of the lesson. That'll come up really in one of the last few slides. All right. So we look at this, and this is, to me, a reminder of what we've talked about over the last 2 weeks since school started, and that's that your note-taking needs to be personal, meaning that it needs to be something that works for you, but it should also be efficient and effective. Efficient, meaning it shouldn't take you too much time. You shouldn't have to pore over every single word of every single text that you read in your notes. You should be able to pull out information, and it should be effective in that you should be able to pull out the most useful information to you. All right, so you want to be able to find the words and the phrases and the dates and the facts that are going to be useful for you as you take assessments going forward and as you try to master these concepts. So one of the best ways to do that is via a mind map, and I know we've talked about mind map note taking in the past, but a mind map essentially looks like this. It's an opportunity for you to represent concepts and phrases in a diagram of some sort. So in this case, we've got a diagram. The topic is organic compounds in living organisms. So based on your notes, I want you to just ask yourself. You don't have to say yes or no. You don't have to tell me. You don't have to tell anybody else. But be honest with yourself. If you have your notes out right now, could you fill out this diagram based on what you have in your notes? Obviously, I hope the answer is yes, because we've covered everything that you would need to complete this diagram. But if the answer is no, then that doesn't mean you should be discouraged. It doesn't mean that you are a bad person or a bad student. It just means that you have a little bit more work to do. And one of the ways that you can get that information is by watching some of the previous lessons, and also by dedicating and committing yourself to taking efficient and effective notes going forward. All right, so these mind maps, I think, are always a good exercise for you to test your knowledge and to see if you are able to make the correct connections between concepts. But if your preferred method of note taking is an outline, or if it is Cornell notes, or if it looks like something else, then you are more than welcome to do that note taking. So note taking should just be personal. It should be what works for you, and it should also be efficient and effective. That's what you all should be thinking about as you become stronger note takers. All right. So jumping into the lesson, please make sure you have your notes out, whatever form they may come in. And the biology teachers and I, there are two other biology teachers, Ms. Baxley and Ms. Fields. We are trying to emphasize the information that, I see you, Kyrie, thanks for joining us. We are trying to emphasize the information that we know you all should be writing down by highlighting it. So for those of you who weren't here in past days, please make sure that when you go back and look at the lessons, you're really focused on the words that are highlighted, typically in yellow, but sometimes they'll be written in red, but in some way they'll stand out. So in this case, it says enzymes are specific because they each have a unique shape, which is caused by sequence and folding of amino acids. So the words we need to focus on here: enzymes, specific, unique shape, and amino acids. I'm going to talk about each of those a little bit more. I do want you all to know that RXN is shorthand for reaction. I sent that to the chat. Okay, but this first sentence is telling us that enzymes, which are responsible for speeding up chemical reactions, enzymes are proteins, and so that means they are made of amino acids. Of course, you all know at this point that amino acids are the monomers for proteins, aka amino acids are the building blocks for proteins, aka amino acids are the subunits for proteins. Okay, so I need amino acids to make proteins.
Mr. Rudd,
Yes.
my phone is on 11% and I'm in the car and it's about to die.
Okay.
And I just don't have my charger.
Okay. If you end up dropping out, then you'll just have to watch the rest of the lesson when it gets uploaded to Canvas. No big deal there.
Okay.
All right. But we also want to focus on the fact that enzymes are specific, which means that they have a unique shape and they can only work with other unique things. So one enzyme is not one size fits all. It's not a fitted cap here. One enzyme can only work for one other substance, typically, maybe one or two. But the shape matters. The shape is extremely important. Our second sentence says enzymes work with only one substrate or reactant. The substrate must fit into the active site for the reaction to take place. We've got a fun GIF, whatever you want to call it, down there at the bottom right, that really illustrates what that second sentence is talking about. The enzyme is the Pac-Man looking figure, the orange figure. And the mouth of the Pac-Man would be considered the active site. It's called the active site because that's where the reaction takes place. That's where the action is. And then we see this little blue pie-shaped figure that just fits directly into the active site of the enzyme. So if we imagine that this substrate was shaped like a square and not a piece of pie or a triangle, then obviously it wouldn't fit well into the active site. Or if our active site was shaped like a circle, then obviously this pie wouldn't fit well with the enzyme. So they have to be meeting each other in a way that corresponds to both of their shapes. So the enzyme's shape is extremely important. Okay. Enzymes are catalysts. They speed up chemical reactions by lowering the activation energy. And the activation energy is the energy needed to start the reaction. We're going to see an image that illustrates this pretty well. But I want you all to take some time to write this sentence down. Enzymes are catalysts. They speed up chemical reactions by lowering the activation energy, the energy needed to start the reaction. While people are writing, I also want to take this opportunity to remind you all, if you need anything, it doesn't have to be related to biology. It doesn't even have to be related to school. But if you need anything and you would like to talk with me about it, you can schedule an appointment with me at that link that I just sent to the chat. I have time reserved every day, specifically to talk with students. All I ask is that you try to schedule an appointment at least a day in advance. That way other students won't have the opportunity to sign up. Okay, so I know there's a lot going on in society. There's a lot going on in your lives as young people. There's a lot going on in your lives as high school students. So if there's anything that I can do to support you or to take things off of your plate or just help you think through whatever is going on in your head, please just let me know, and we can find some unique strategies to make things work for you. All right. So enzymes are catalysts. That just means that they speed reactions up. But the way that they do that is by lowering the activation energy. And this is somewhat of a complicated concept. So I'm going to walk through this slowly. So just take some time to just look at this graph, come to some conclusions or some ideas about what it is saying. Try to apply the sentence that's above the graph to the graph, meaning try to see if you can see those words also located in the graph, and then I'll talk about it. So take 10 seconds just to break that down to yourself. Okay. So some of you have a background in chemistry, either because you've taken chemistry already or just because you may have heard some of the chemical concepts before. And so you've probably heard the words reactants and products, which we can see here in our graph, reactants and products. A reactant is a substance that you start with. So for example, many of you have cars, or people in your family or your friends have cars. Some cars, parts of the car is made out of iron, specifically around the wheel of the car. That iron would be a reactant and a potential chemical energy that could create rust. And that happens when the iron is exposed to oxygen. So the iron is the reactant. That's what we're starting with. And then the oxygen is also a reactant because we're starting with that. And then as they interact with one another, they create a new substance. And that new substance is your product. And that new substance is called rust. So that's just one example of the many, many chemical reactions that you all have witnessed all the time throughout your lives. You just didn't really recognize that what you were watching was a chemical reaction. And we have chemical reactions taking place in our bodies constantly that keep us alive. But the thing about these chemical reactions is that they require energy to get started. I can't really, most chemical reactions are not spontaneous, which means that they don't just happen automatically. They require some initial input of energy. And that initial input of energy is called the activation energy. The analogy that I like to use, again, I've got my reactants down here. These are my starting substances. And I've got my products over here. These are what I produce. They are my final substance, my final product. I like to think about there being a ball right next to the reactants, kind of at the bottom of this hill. This looks like a hill, right? So let's just imagine that there's a ball here at the bottom of the hill. If I only gave this ball just a little shove, maybe it makes its way up that high. And then, of course, gravity is going to pull it back down. So it'll just roll back down the hill. If I give it a stronger shove, maybe it makes its way all the way up here, but still not enough energy. I didn't put in enough energy to get it to the top of that hill. Now, my goal, of course, is to get it from this side of the hill to the other side of the hill. So let's say that DeMarco and I are playing a game. I'm in the reactant side, he's in the product side. And the only way that I can get this ball to DeMarco is if I get it over this hill. So I've got to give it a good shove. I've got to put a lot of energy into this ball to get it all the way to the top of the hill. But once it gets here, gravity is going to pull it down the rest of the way to DeMarco. So all I have to do, I don't need to give it enough energy to get to the top of the hill and roll down. The rolling down part is going to happen by itself. I just need enough energy to get to the top of the hill. And as soon as it gets to the top of that hill, it's going to roll down. At the top of the hill is where the chemical reaction takes place. And my reactants start to turn into products. But I can only get to that point if I put enough energy in. And that energy is called the activation energy. It's the energy I need to activate the reaction, the energy I need to start the reaction. Okay? So you've got to get to the top of the hill to start the reaction. The cool thing about enzymes, we should notice that there are two distinct hills here. The cool thing about enzymes is that you don't need as much energy to get over the hill with an enzyme because the hill is much shorter now. So instead of having to put 100% of my energy and my strength behind the ball to get it over to DeMarco, all I need to do is give it 60% of my energy to get it over this much shorter hill because I have the help of an enzyme, and now it'll roll back down to DeMarco. So activation energy is what I need to actually start the chemical reaction, to get it to the top of the hill so that the reaction can begin. But once the reaction begins, the ball just starts to roll and we eventually get to the products. An enzyme makes it much easier for that reaction to take place because it lowers the amount of energy that you need to put in. Any questions about that? Because I know that can be a complicated concept. Okay. The asynchronous assignment for the day will help to explain that concept even more. So if you're confused and you just need to hear it from someone else, that video hopefully will help you out. But again, if you're confused about not only this, but other things that we've talked about so far, you might want to schedule an appointment to meet with me one-on-one so that we can get all your questions answered. Don't wait until it's too late to start trying to go to tutorials and get the help that you need. Start now. Start where you are, use what you have, do what you can. All right. So our bodies undergo chemical reactions all the time. The process of converting the sugars that you eat into energy is a chemical reaction. Many of the defenses that our bodies have against pathogens like bacteria and viruses and poisons, those require chemical reactions. The process of breaking down the fats that you eat or that your body stores, that's a chemical reaction. So these happen all the time. The problem is, without enzymes, they would be happening very slowly. So enzymes are what allow our bodies to do these chemical reactions faster in a way that allows our lives to carry on. If we had to wait 2 days for the sugars that we eat to be converted to usable energy, we would never be able to do anything. But the enzymes in our bodies and in your stomach and in your intestines, those enzymes allow us to absorb that energy and use it much faster. All right, so the analogy that we use, a guy who's kneeling down just trying to spark a fire by himself using a flint or a stone and some wood, it's going to take a while, right? You've got to be pretty skilled at doing that. But if we just simply use gasoline on a spark, it can create a giant flame very, very quickly. Hopefully we don't have any pyros in the class who have some new ideas now. But enzymes are similar to that. They speed these reactions up, so they're similar to the gasoline. One of the other most important qualities of enzymes is their reusability. An enzyme does not change shapes in the course of a reaction, which means that I can put an enzyme into a reaction and I can expect to get that same enzyme back out once the reaction has completed. That's good because it means that the enzymes don't get used up. I can use that exact same enzyme for my next reaction. And then when that reaction is done, I still have that same enzyme and I can use it again and again and again and again, and so on and so forth. So as long as you do not change the shape of the enzyme, then it's still going to be usable. But the moment that that shape changes, and we're going to talk about this in a few slides, the moment that the shape changes, the enzyme is probably no longer usable. So we've got an image here that I'll talk about briefly, and then there's a question on the next slide. The description says amylase gets a starch molecule, digests it into maltose, and it's ready to do it all over again. So what we're seeing is amylase is an enzyme, this big green thing. That's your enzyme. This enzyme specifically is used to break down starch, which is represented by this red chain here. So as amylase breaks down starch, as we can see, all these chains get separated. What's created is called maltose. So in this case, can someone tell me what is the reactant? What is the starting product, or what's the starting substance in this image? I'll give you a hint. It rhymes with start.
What was the question?
What is our starting reactant in this diagram here?
Heart.
Fart.
Nard.
Starch,
Am I
yeah.
being childish?
Starch is our reactant. That's what we're starting with. But what are we ending up with? What's our product?
Did I say maltose or something?
Yes, yeah, maltose is our product. So we start with starch, but the starch gets digested, it gets broken down, and we end up with maltose. So that's a chemical reaction. And the enzyme allows that chemical reaction to happen quickly. But you see, the enzyme doesn't change. It looks the same at the end as it did in the beginning. Okay. So same diagram. Hopefully you have your notes from the past few days. Based on the diagram below, starch must be which type of biological molecule?
Lipid.
Heard someone say lipid. Anybody else think anything else? Let's see. Who was on the call yesterday? Fanique, Nevea, DJ.
Is it A?
It is.
I'm tripping. It was a carbohydrate. I said lipid.
Good. Starch is a carbohydrate. Now, we know that because we've talked about it over the last few days, but we can also look at this image and get a hint as well. The hint is that we've got maltose. What do you notice about that word that is the hint?
OSE.
Excellent. Excellent.
Toast.
Maltose ends in OSE. And anytime we see OSE, what should we be thinking about?
Carbs. Carbohydrates.
Not specifically starch, but just in general, we should be thinking about sugars. We should be thinking about carb. Oh, you said carbs. Okay, I'm sorry, Joseph. Yeah, you're 100% correct. When we see OSE, we should be thinking about carbs. Okay, so maltose is a carbohydrate, which must mean that if starch is just broken down into maltose, then it must also be a carbohydrate as well. If I break down a lipid, I don't end up with a carbohydrate. If I break down a nucleic acid, I don't end up with a carbohydrate. The only thing that can give me a carbohydrate is another carbohydrate. So starch must be a carbohydrate in this case. So I appreciate the teamwork in getting to that answer. Okay. So enzymes have really two uses for the purposes of this class. If you take a more advanced biology class, you'll learn about some of the other functions that enzymes can serve. But the slide says enzymes are used to digest large molecules into their monomers, then use them to synthesize new molecules. Now, I want to be careful here. I'll say why. I'll give you some time to write. Okay. I want to be careful here because typically it is not the same enzyme that is doing both the digesting and the synthesizing. We typically need different enzymes to do those things. Just like the cells in our bodies all have a specialized or specific job that they do, enzymes have a specific specialized job that they do. Meaning the cells that allow me to see are not the same cells that allow me to taste and they're not the same cells that allow me to touch things and feel things. I have different cells for each of those processes, and they each do a specific job. Enzymes are the same way. We've already talked about the fact that enzymes are specific because of their shape, and that means that they do one job and they do it very well, and they do it all the time. They're just constantly doing it. Okay, so if we picture an assembly line, if you've ever seen an assembly line or you've heard about the assembly lines where cars get built, one person just stands in the same place and they just do the same thing every day. They just wait for that conveyor belt to come and they just nail something in, or they screw something in, or they lift something up and place it. And they're just doing that same exact job. And the reason for this is that it's more efficient. If I don't have to train someone to do 100 different jobs, but I can just train them to do one job and do it really well, then that's going to be, and then I get 99 other people to do the other 99 jobs, that's more efficient. I can get much more done. Enzymes and most living organisms function in the same way. We want to be able to be as efficient as possible. So these enzymes digest things, which means that they can break them down. But then I need another enzyme to synthesize something, which means to build it. So I'll type that into the chat. Excuse me. Synthesize. We've been introduced that word already, but synthesize means build. Digest means to break down. Keep in mind, once an enzyme goes through a chemical reaction, it can still be used. It's going to come out of the chemical reaction in the same shape if everything goes well. Okay. All right. So specific enzymes are used for specific compounds. Specific enzymes are used for specific compounds. All right, so I'm going to need some participation here. Hopefully I hear some new voices. Joseph, I appreciate you. Marco, I appreciate you. Jaden, I think I've heard from you as well. So let's get some new voices as well. And Fanique, I think I heard from you too. So protease breaks down proteins into what? If I have a protein and I break it down, what should I be left with? I'll give you a hint. We're looking for the monomer of a protein here. So a protein is the polymer. If I break that down into a monomer, what should I be left with? What did you say, Joseph?
Amino acid.
Yes, exactly. And can you tell me how you knew that?
Well, to be honest, I thought since you said protein is a monomer and amino acid is basically like what we use. So I just thought it would be an amino acid. And I went back over my notes too.
Good, excellent. And that's a good habit to be in, guys. He just said something that's really important. Don't overwork yourselves. Make sure that the answers are right there for you. So if proteins are the polymer, then the monomer that they get broken down into is amino acids. That's what we've been talking about for the last 2 days. Excuse me. All right, let's try another one. Amylase breaks down carbohydrates into what? Aaron, do you have any thoughts? Do you know what carbohydrates would be broken down into? Not amino acids. That's amino acids are for proteins.
Not starch.
Not starch. Starch is an example of a carbohydrate, but what is the monomer of a carbohydrate?
Is it glucose?
Thank you, Nick. Thank you, Brian. Yes, glucose. Amylase gets broken, or I'm sorry, amylase breaks down carbohydrates into glucose because glucose is the monomer of carbohydrates. So we've really got to wrap our heads around this, guys. So amino acids are the monomer proteins. Glucose is the monomer, I'm going to put in parentheses, aka monosaccharide. It's the monomer carbs. All right, so following that same logic, it says deoxyribonuclease breaks down nucleic acids into what? What would be the monomer of nucleic acids? What's the monomer of a nucleic acid?
How you pronounce that word?
Just spell it. You can type it into the chat.
I'm talking about that D word.
Oh, deoxyribonucleic.
Do they break down into nucleotides?
Yes, thank you, Ryan. So nucleotides are the monomer of nucleic acids. So it says deoxyribonuclease breaks down nucleic acids into nucleotides because nucleotides are the monomer of nucleic acids. Last one, we should already know, we should be looking for the monomer here. Lipase breaks down lipids into what? Okay, so that last question there, we're looking for. Go ahead, Brian.
Is lipids fat or?
Yes,
lipids
lipids are.
fat, right?
Yeah, fats are an example of lipids.
Okay. All right, I'm gonna think on that. Hold up.
Nick, thank you. You got one part of it. Glycerol. What's the other part of the monomer? We're looking for the monomer of lipids. So glycerol is one part. What's the other part? Thank you, Alyssa. Fatty acid. We should have fatty acid tails. Good. 3 of them. So the monomer of a lipid is glycerol and 3 fatty acid tails. So if you don't have that written down, I mean, hopefully you have that entire table, but if you don't have that information written down somewhere, I'm really asking you to take some time to write that down. I've typed everything into the chat. Okay, and then the question at the bottom says, what do all of these enzymes end in? Someone be observative.
It's all the acid.
Okay, they're not all they're not all acids, but as Alyssa just put into the chat, they all end in ASE. So if you remember, sugars end in OSE. And I think, Joseph, you told us that earlier. Enzymes end in ASE. Most enzymes do. So this is how we can start to build our repertoire. This is how we can start to make connections between concepts. So when I see something on a test or on a quiz or in an assignment, and it ends in ASE, automatically my mind should be thinking about enzymes. Or when I see something that ends in OSE, I should be thinking about sugars. And I should know sugars are carbohydrates. And I should know carbohydrates are made of glucose, right? So I can start to make those connections. The more I work to see those connections and to break down that table and to see the similarities and differences, the less I will have to work to make the connections when it comes time to, when I'm asked for them. Okay, so 10 to 15 minutes a day, look at that table and break it down. And that should take you a long, long way. All right, oops. Okay, 2 more slides. I'm going to pause here for about 4 minutes until 1 o'clock to give you all the opportunity to draw this into your notes for people who are writing. Otherwise, you can take a picture of it or you can screenshot it, but this is an important image. Because it shows every part of this chemical reaction. We've got C, which is the purple shape here. And that's your enzyme. Notice something. C looks the exact same at the beginning as it does at the end. Okay, so enzymes do not change over the course of a chemical reaction. We also see that this enzyme has an active site, which is really, it's like the mouth. It's where the substrate goes in. It's where the action takes place. And here's your reactant, aka your substrate. It's going to go into the active site of the enzyme. And the enzyme in this case is digesting it. It's breaking it down. So what starts off as one substance, as a reactant, ends up as 2 different substances, 2 different products, because the enzyme is breaking it down. And then, like I said, the enzyme comes out looking exactly as it did in the beginning. So that means that this same enzyme can then go right back and it can be used to break down another substrate. Okay, 2 more minutes to draw that.
Shady big lip ass.
Joseph, you ugly. You ain't no girl on my money, you know.
Nigga, you want to check my DMs, bro? You could see my fucking shorties at Apple.
You
Bitch,
trying to get
nigga.
Shut up.
Man, Kyrie, shut your coconut head up, bro.
Who is that talking? I know that ain't DeMarco.
No, it's Joseph. Get Joseph. Bro.
I know that ain't Joseph. I know it's not Joseph.
Okay. Let's finish this up. All right. So 1 more slide, and then I'll introduce you all to the asynchronous assignment. We only have 20 more minutes. But enzymes, if they change shape, then their function changes. Okay, so shape determines function. I left off an S there. Let me correct that. All right, so shape determines function. If I change the shape, then I change the function. And the shape of an enzyme changes when it is denatured. That's what denature means. The active site changes shapes. And that means it's no longer going to work in the same way, and it might not work at all. Enzymes, therefore, have to exist in a very specific and controlled environment. They don't like when things are unpredictable or when things are erratic and they're constantly shifting. Enzymes work best when they are in a very specific environment. So we need to pay attention to the pH scale. And this really should say, it doesn't go from, well, I guess it does. Okay. So we need to pay attention to the pH scale, which runs from 0 to 6. I'm sorry, from 0 to 14. But we also need to be thinking about temperature. So let's look at what this actually looks like. We've got two enzymes here. One is called pepsin and one is called trypsin. These are real enzymes that you have in your bodies right now. One of them is in your stomach. Pepsin is in your stomach, so it allows you to break down foods specifically for carbohydrates. And trypsin is in your intestines. And so it allows you to break down foods specifically for the lipids. And as we can see, these enzymes are a little bit different. Each one of them has an optimal pH. So that optimal pH is where they really prefer to work. Pepsin clearly prefers to work at a pH of about 2. So it likes an acidic environment. It likes to be around acids. Trypsin has an optimal pH of about 8. So it likes a more neutral, but a more basic environment. The way that we can tell where they really like to be, well, obviously in this image, we've got the arrows telling us. But the optimal point is where the graph is the highest, where the curve is the highest. So I want to find the highest point on that curve and then drop it down and figure out which pH am I looking for. I find the highest point on the curve, and then I drop it down and figure out which pH am I talking about. Now, it doesn't only work at that specific pH. Pepsin does not only work at a pH of 2. Trypsin does not only work at a pH of 8. That's where they prefer, but they can also, pepsin can also work at a pH of 1. It can also work at a pH of 3. But we notice that it's not working very well. Okay, so if the graph is lower, what that represents is that the enzyme is not working well. The reaction time is slower. And eventually, we get to the point where pepsin just no longer works anymore. Right at about 3.5, pepsin is no longer working. Okay. For trypsin, again, its optimal pH is about 8. But as I move down the graph, it's not working as much. And then once I get to about 5.5 here, it no longer works at all. Or as I get to about 10 over here, it no longer works at all. All right, so that's what these graphs tell you. And you want to be able to do the same thing for temperature as well. So we could imagine that instead of pH on your x-axis down here, we had temperature. Okay, so your asynchronous assignment, we've got 15 minutes. That should be enough time to complete it, is to watch an Amoeba Sisters video and take a quiz as you watch the video. The quiz is just going to ask you 7 questions, and they're in order. So the questions that are asked at the beginning of the quiz will be at the beginning of the video. Then the next question will be a little bit later in the video, and so on and so forth. But it's going to explain some of these concepts that we've been talking about today regarding enzymes. And I think it'll be beneficial to you all. So that's what you should go ahead and knock out right now. We got 15 minutes. That should be plenty of time. I'll type it into the chat as well. If you have any questions, please just let me know. I'll put myself on mute.
Chelsea, ugly. Joseph, you ugly as shit. Kyrie, you ugly as shit. And tomorrow,
The fuck
all
up.
ugly.
Because
My,
you was
my
ugly.
camera not even on. Dude. Shut up. You weird.
Debating to shut up his big lip clapping too motherfucking much. Goddamn.
What? What?
Don't make no sense. What time class in? And what we do when we get out? When we get done with all of it?
We have 2 more minutes, less than 2 minutes. When you're done, I mean, if you've done the exit ticket as well, then you're good to go. If you've done the exit ticket and the Amoeba Sisters video, you're good to go.
All right. You better leave, Kari. For sure. All right, peace, bro. Jaden.
What?
Bro, you got PS4, bro?
No, bro. I got Xbox, bro. You already know.
You got a fat box. King.
Freaking PlayStation.
DeMarco
Garbage.
suck. Marco suck.
DeMarco trash. We know.
Joseph, you got a game? What you play on?
He left,
Oh.
but he ain't got no system.
Oh.
The only thing he got a house.
Okay, folks, it's 1:20, so you all are good to go. I hope you have an excellent weekend. Hope you get some rest and you're also productive with your time. Spend some time with your families if you can. Get some time outside. I will talk to you on Monday.
All right. DeMarco.
All right, with you. Thank you.
DeMarco.